cipher files. So the archaea tend to be more of an extreme organism. The archaea, that phylum, is more diverse in the types of organisms that we find there. Now there are two other phyla, the nanoarchaea, which are teeny tiny little archaea, and as of yet we only know of one genus, and another phylum called the archaea. And the archaea, they've actually never been able to culture an organism in this phylum. They only know that it exists because they have found DNA sequences in the environment that don't match up with any of the other phylums. They know they're archaea, but they don't match with the archaea, the archaea, or the nanoarchaea. So they made this new phylum called the archaea, which is a new phylum, just recently been added, and pretty much all we know is that they exist. That's all we know pretty much about those organisms. But I want you to be familiar and know these four different phylum names, so the archaea, the archaea, the archaea, and the nanoarchaea. And just to, again, sort of give you a little bit of the characteristics about the archaea, this is a table from your book that compares them to the other organisms, to bacteria or to eukaryotes. So their cell type is prokaryotic, so they have sort of the typical things we associate with prokaryotes. They don't have a nucleus, they only have ribosomes, things like that. Their genetic material is similar to a bacteria, so it's single and circular, so they have one chromosome typically, and it's circular. Now, their ribosomes, size-wise, are the same as bacteria, but internal structure has shown that they're actually more similar to eukaryotes. And that's because they share some of the same ribosomal RNA sequences as the eukaryotes do. So they actually have a number of, 3 of them actually, are the same as the ones we find in eukaryotes. And how they produce proteins is also similar to eukaryotes. And so this may reflect the lineage that they come from. Remember that the archaea splintered off the eukaryotic line fairly long ago, but even still, they're more closely related to eukaryotes than they are to bacteria. They usually don't have true peptide glycan. Remember that the ones that do have the cell wall will have the NAT instead of NAM. And we can also differentiate them because of their cell membranes, because they have the ether linkages in their phospholipids as opposed to the ester linkages that we see in bacteria or in eukaryotes. So just kind of familiarize yourself with the sort of the major characteristics. And just to kind of give you a little list of some of the things we find in them, we find examples of both chemoorganotrophs and chemolithotrophs. There are some that can fix carbon. You have aerobic and anaerobic ones. Remember that they don't have true peptide glycan, and most of them, there aren't any real sort of true photosynthetic forms either. Although they actually think they might have found some. They have the unusual lipids, and then you have these extremophiles. So a lot of this is stuff I've shown you before, but it bears repeating. So for those organisms that do have a cell wall, remember that they have the beta-1,3 linkage, so they have the different linkage than what we see in bacteria, and we also have NAT here instead of NAM. So the NAM residue that we normally see in bacteria is substituted with a similar but different sugar, and it's bonded to the other sugar differently. And so this isn't true peptide glycan, but it's similar to it. But keep in mind, not all archaea have these. Some do. Some will have a cell wall. But some don't have cell walls. Instead, they just have proteins or glycoproteins that form kind of a protective layer. But again, this is just how they differ from the cell walls in bacteria. And then I've shown you this before too. This is the cell membrane. So this is what we see in bacteria and eukaryotes. So here is the phospholipid. Here's my glycerol here. Here's my phosphate head. And then these would be my 2 fatty acid tails. Well, in bacteria and eukaryotes, remember that the fatty acids are connected by an ester bond here. But in the archaea, it's an ether bond here. So here again is my phosphate head. Here's my glycerol. Here's my fatty acid tails. We have an ether bond here. And oftentimes the R group, or the fatty acid tail itself, is repeated. It's this structure here, which is called isoprene. And you have this sort of regular repeated structure. So we have this, and then And so that leads to a very characteristic shape of the fatty acids of the archaea, especially those that are heat tolerant, especially those that are thermophilic. And so if we look at the fatty acids, and these are going to be within some of the thermophiles. So again, here's my phosphate head here, here's my glycerol, and here's my fatty acid tails. So here's my ether linkage here. But because you've got this repeated double bonding every other carbon with the isoprene, you get these regular bends, these regular kinks in the fatty acid tails of the phospholipids within the membrane. And so if you sort of look at the traditional phospholipid membrane here, again, here's the phosphate head, here's the glycerol part, here's the fatty acid tails. So the internal part here is going to be hydrophobic, the external part is going to be hydrophilic. So this part will engage water, this part will repel water. But because you've got this regular sort of zigzag pattern, this regular bending, the phospholipids can get really close together. They can pack in really tightly because they're all bending in the same position. So if I say, for example, I took this phospholipid, I could actually move it up and snuggle it up against the fatty acid underneath it. So you can actually pack them in really close. And what that does is that increases the melting point of the membrane. Because remember, the membrane's made up of fats mostly, and what happens when you heat up a fat? It melts. I mean, take butter. If you have butter at room temperature, it's a nice stick of butter. Throw it in a hot frying pan, and what happens to it? It falls apart. It melts. And so by stacking together these membranes, by the phospholipids packing in really tightly together, that increases the melting point. And so a lot of thermophiles will have this type of membrane because it won't melt at the high temperatures that they live in, because they're really sort of packed tightly together. And so the heat doesn't penetrate down into the membrane, it increases the melting point. Now some of the extreme thermophiles in the archaea take that even a step further, and they actually connect the phospholipids on both sides of the membrane. They connect them in the hydrophobic interior. And so again, we had a phospholipid over here, here's my phosphate, here's my fatty acid tails. If I've got another one on the other side of the membrane, again, because you've got this regular zigzagging, this regular bending and kinking, they can actually form bonds between the fatty acid tails, and that produces what's known as a lipid monolayer. And so here again, here's my phosphate head, here's my glycerol, and here's the fatty acid tails. They're joined together in the hydrophobic interior of the membrane. That's even more heat tolerant than the one above it. And so for the extreme thermophiles, for the organisms that are living at 400 degrees Celsius in the hydrothermal vents in the bottom of the ocean, they have these kinds of membranes because they're extremely heat tolerant. They don't melt at the high